Hello everyone, my name is Amit Khan. In this video, I will discuss about measurement of voltage, current, energy and power. It is a topic of electronics measurement. Now first comes the rectifier type instruments. The construction and working principle is the rectifier type instruments measures the alternating voltage and current with the help of rectifying elements and permanent magnet moving coil type of instruments. However, the primary function of rectifier type of instruments work as voltmeter. Now, one question must arise in our mind: why we use rectifier type of instruments widely in the industrial world, though we have various other AC voltmeter like electrodynamometer type instruments, thermocouple type instruments, etc. The answer is the cost of electrodynamometer type of instruments is quite high than rectifier type instruments. The thermocouple type instruments are more delicate than the rectifier type instruments. Before we look at the construction principle of and working of rectifier type instruments, there is need to discuss in detail about the voltage current characteristics of ideal and practical rectifier element called diode. So let us first discuss the ideal characteristics of a rectifying element. Now, what is an ideal rectifying element? A rectifying element is one which offers zero resistance if it is forward biased and offers infinite resistance if it is reverse biased. This property is used to rectify the voltage like AC to DC. So rectification means to convert an alternating quantity into direct quantity. So in the circuit diagram, the ideal diode is connected in a series with the voltage source and load resistance. Now, when we make the diode forward biased, it conducts perfectly, offering zero electrical resistance path. Thus, it behaves as short-circuited. Then we can make the diode forward biased by connecting the positive terminal of the battery with anode and negative terminal with cathode. The forward characteristics of rectifying element, which is diode here, is shown in the voltage current characteristics. Now, when we apply negative voltage, that means connecting the negative terminal of the battery with the anode terminal of the diode and positive terminal of the battery to the cathode terminal of the diode. Due to this reverse bias, it offers infinite electrical resistance and thus it behaves as an open circuit. So the complete voltage current characteristics are shown in the figure. We can see the voltage current characteristics in the diagram. So if you consider the same circuit, but the difference is here we are using the practical rectifying element instead of an ideal diode. So in practical rectifying element, he is having some finite forward blocking voltage and high reverse blocking voltage. We will apply the same procedure in order to obtain the voltage current characteristics of practical rectifying element. Now, when we make the practical rectifying element forward biased, it does not conduct till the applied voltage is not greater the forward breakdown voltage, or we can say that is called knee voltage. When the applied voltage becomes greater than the knee voltage, the diode will come under conduction mode, thus behaves as short circuited, but due to some electrical resistance there is a certain amount of voltage drop across this practical diode. We can make the rectifying element forward biased by connecting its positive terminal of the battery with the anode and negative terminal with cathode. The forward characteristics of practical rectifying element of diode is shown in the voltage current characteristics. Now, when we apply negative voltage, that means connecting the negative terminal of the battery with the anode terminal of the diode and the positive terminal of the battery to the cathode terminal of the diode. Then, due to reverse bias, it offers finite resistance and the negative voltage till the applied voltage becomes equal to the reverse breakdown voltage, and thus it behaves as open circuit. The complete characteristics are shown in the figure. In the figure we can see the knee voltage, the forward biased condition, reverse biased condition, and we can see also the reverse breakdown voltage. This is the ideal voltage current relationship of a practical diode. Then comes half wave rectifier circuits of rectifier type instruments. So let us consider the half wave rectifier circuit given below, in which the rectifying element is connected in series with a sinusoidal voltage source, permanent magnet moving coil instrument, and the multiplier resistor. Here we can see the circuit diagram, which consists of a multiplier, a diode, PMMC, and a PMMC instrument, that is permanent magnet moving coil instrument. The function of this multiplier electrical resistance is to limit the current drawn by the permanent magnet moving coil type of instrument. It is very essential to limit the current drawn, because if the current exceeds the current of PMMC, then it destructs the instrument. Then here we divide our operation into two parts. In first part, we apply constant DC voltage to the above circuit. In the circuit diagram, we are assuming the rectifying element as ideal one. Let us mark the resistance of multiplier be R, and that of the permanent magnet moving coil is R1. So the DC voltage produces the full scale deflection of magnitude I equals to V divided by R plus R1, where V is the root mean square value of voltage. And in the second case, we will apply AC sinusoidal AC voltage to the circuit. So V equals to Vm sin omega t, and we will get the output waveform. In the positive half cycle, the rectifying element will conduct, and in the negative half cycle, it does not conduct. So we will get a pulse of voltage at moving coil instrument, which produces pulsating current. Thus pulsating current will produce pulsating torque. The deflection produced will correspond to the average value of the voltage. So the V average is 1 by 2 pi integral 0 to pi Vm sin omega t dt, that is equals to 1 by pi into Vm. So V average equals to 0.545 volt. Here the input output waveform is given in the diagram. So we can conclude that the sensitivity of the AC input is 0.45 times the sensitivity of DC input in case of half wave rectifier. Then comes full wave rectifier. We can see a full wave bridge rectifier in the circuit diagram, consisting of a PMMC instrument, PMMC meter, and a multiplier. It has 4 diodes. The full wave bridge rectifier contains 4 diodes. Here we divide our operation into two parts. First case, we analyze the output applying the DC voltage, and in the another we apply AC voltage to the circuit. A series multiplier resistance is connected. So in the first case, the full scale deflection will be V divided by R plus R1, where V is the root mean square value of the applied voltage, R is the resistance of the resistance multiplier, and R1 is the electrical resistance of the instrument. The R and R1 are marked in the circuit diagram. And in the second case, we will apply AC sinusoidal voltage, that is V equals to Vm sin omega t. Vm is the peak value of the applied voltage. Again, if we calculate the value of full scale deflection current, in this case, by applying the similar procedure, we have done in the half wave rectifier, then we will get here the full scale current as 9V divided by R plus R1. Here V average equals to 0.9 volt. So thus comparing it DC output, we conclude that sensitivity with AC input voltage source is 0.9 times as in the case of DC input voltage source. the input output waveform of a full wave rectifier is given in the in the diagram. Then comes the factor which affect the performance of rectifier type instruments. Rectifier type of instruments is calibrated in terms of root mean square values of sinusoidal wave of voltage and current. The problem is that the input waveform may or may not have some same form factor on which the scale of this meter is calibrated. Then there may be some error due to the rectifier circuit, as we not include the resistance of the rectifier bridge circuits in both the case. Then there may variation in the temperature, effect of capacitance of the bridge rectifier. The sensitivity of rectifier type instruments is low in case of AC input voltage. So these are the factors which affect the performance of rectifier type instruments. Then comes the advantages of rectifier type instruments. The accuracy of rectifier type instrument is about 5% under normal operating condition. The frequency range can be extended to high value. They have uniform scale on the meter. They have low operating value of current and voltages. Then applications of rectifier type instruments are they are used for measuring the voltage whose range lies between 50 to 250 volt. It uses a milliammeter and microammeter. Rectifier instruments type instruments used in the communication circuit for measurement. The disadvantages of rectifier type instruments are the sensitivity of rectifier type instrument is low in case of AC input voltage. Effect of temperature change is also a disadvantage of rectifier type instrument. Then comes electrodynamic wattmeter or electrodynamometer wattmeter. The instrument whose working depends on the reaction between the magnetic field of moving and fixed coil is known as electrodynamometer wattmeter. It uses for measuring the power of both AC and DC circuits. The working depends on the theory that the current carrying conductor placed in a magnetic field experiences a mechanical force. This mechanical force further deflects the pointer which is mounted on the calibrated scale. So if we come to the construction of an electrodynamometer wattmeter, then it consists of a fixed coil. The fixed coil connects in series with the load. For making the construction easy, the fixed coil is divided into two parts. The fixed coil is considered as a current coil. Then comes the moving coil. The moving coil is considered as the pressure coil of the instrument. It connects in parallel with the supply voltage. The pointer mounts on the moving coil. Then comes the control. The control system provides the controlling torque to the instruments. The gravity control and the spring control are the two types of control system. The spring control system is used for the movement of the pointer. Then comes damping. Damping is the effect which reduces the movement of the pointer. In this wattmeter, the damping torque produces because of the air friction. Then comes scales and pointers. The instruments use a linear scale because their moving coil moves linearly. The apparatus uses the knife edge pointer for removing the parallax error which causes because of oversights. Then comes the working of electrodynamometer wattmeter. We can see the diagram of a electrodynamometer wattmeter. We can see the fixed coil, the moving coil, the pointer. So here we can also see the construction. It is the diagram of electrodynamometer wattmeter. So if you come on the working principle, it has two types of coils, fixed and moving coil. The fixed coil connects in series with the circuit whose power consumption used to be measured. The supply voltage applies to the moving coil. The resistor controls the current across the moving coil and it is connected in series with it. The pointer is fixed on the moving coil, which is placed between the fixed coils. The current and voltage of the fixed and moving coil generate the two magnetic fields, and the interaction of these two magnetic fields deflects the pointer of the instrument. The deflection of the pointer is directly proportional to the power flows through it. Then comes the theory of electrodynamic wattmeter. We can see the circuit of electrodynamic wattmeter. You can see the current coil and pressure coil is connected. The instantaneous torque acts on the pointer of the wattmeter is given in the equation, that is T1 equals to I1 into IP into Tm by d theta. IP is the pressure coil current, IC is the current coil current. Dm d theta as the rate of change of deflection of the pointer concerning angle theta. So the voltage across the pressure coil of the circuit is given as V equals to root over 2I sine omega t minus phi. If the pressure coil is purely resistive, then their current is in phase with the voltage and the value of current is IP equals to root over 2 IP sine omega t. If the current coil lag by voltage in phase angle phi, then the current through the current coil is given as minus IP, that is equals to root over 2I sine omega t minus phi, as it is lagging in the phase angle phi. Then the value of the current is in the pressure coil is very small, so the current flows through the pressure coil is considered as the total load current, and the torque acts on the coils becomes Ti equals to root over 2 IP sine omega t minus phi into dm d theta. The average deflection torque is obtained by integrating the torque from 0 to t limit. So the average deflection torque is equals to root over 2 Vi by Rp cos phi dm by d theta, and the controlling torque exerted on the spring is given by Tc equals to k into theta. Then comes the errors in electrodynamometer wattmeter. The first one is pressure coil inductance. The pressure coil has some inductance. Because of the inductance, the current of the pressure coils lags behind the voltage. Then the pressure coil capacitance. This capacitance increases the power factor of the instrument, hence causes the error in the reading. Error due to mutual inductance effect. It has an eddy current error. The eddy current induces in the coil creates its own magnetic field. This field affects the main current flows through the coil. Then stray magnetic field effect. This disturbs the main magnetic field of the electrodynamic wattmeter. It is also a temperature effect. The variation of temperature will change the resistance of the pressure coil. And the calibration of the electrodynamometer wattmeter is same for both the AC and DC measurement. Then comes compensated thermocouple type instrument. The instrument which uses the thermocouple for the measurement of temperature, current and voltage. Such type of instrument is known as thermocouple type instruments. It is used for both AC and DC measurement. We can see the diagram of a thermocouple connected with a PMMC meter. Thermocouple consists of two different metals which are placed in contact with each other as shown in the diagram. First part is called the heater element because when the current will flow through this, heat is produced and thus the temperature will increase at the junction. At this junction, an EMF is produced which is approximately proportional to the temperature difference of hot and cold junctions. The EMF produced is a DC voltage which is directly proportional to the root mean square value of electric current. A permanent magnet moving coil instrument is connected with the second part to read the current passing through the heater. So one question must arise, that why we have used only a permanent magnet moving coil instrument. As because PMMC instrument, the answer is as because PMMC instrument has greater accuracy and sensitivity towards the measurement of DC value. The thermocouple type instruments employ thermocouple in their construction. It can be used for both AC and DC application. Now we will look how the temperature difference is mathematically related to generate EMF at the junction in the thermocouple type of instrument. So let us consider the temperature of the heater element be TA and the temperature of cold meter is TB. Now it is found that the generated EMF at the junction is related to temperature difference, that is E equals to A into TA minus TB plus B into TA minus TB whole square. AB are the constant whose values completely depend on the type of metal. The above equation represents parabolic function. The approximated value of A is from 40 to 50 microvolts, and value of B, constant B, is very small and can be neglected if the air gap field of permanent magnet moving coil is uniform. So we can approximate the above temperature EMF relation as E equals to A into TA minus TB. Here we have assumed that B equals to 0. So the current flowing through the heater coil produces heat as I square R, as we know, where I is the root mean square value of current. If we assume the temperature of cold junction is maintained at room temperature, then the rise in the temperature of the hot junction will be equal to temperature rise at the junction. So we can write TA minus TB is directly proportional to I square R. So TA minus TB, that is equals to K1 into I square into R. Now the deflection angle in moving coil instrument is equal to K into E. So the deflection angle equals to K into A into TA minus TB, as E equals to A into TA minus TB. So we can write K1 into K into A into I square into R, that is equals to K2 into I square, where K2 is the constant. From the above equation we can see the instrument shows the square law response. So this type of instrument shows the square law response. Then comes the construction and working of thermocouple type instruments. We can see the diagram of a construction of a thermocouple type instruments. The major parts are thermoelectric elements. These thermoelectric elements can be of 4 types. First one is contact type. It is a separate heater. The action of thermocouple type instrument can be explained as at the junction of electrical energy is being converted to thermal energy in the heater element. A portion of the heat is transferred to the hot junction while most of the heat is dissipated away. This is shown in the figure. A heat and then the heat energy which is transferred to the hot junction is again converted to electrical due to Seebeck effect. Only a portion of electrical energy is converted into mechanical energy, which is used to produce deflecting torque. So there is a requirement of highly accurate sensitive DC instrument. So the contact type is given in the figure. Then comes the non-contact type. In non-contact type there is insulation between the heating element and the thermocouple. That means there are no direct contact between the two. So this type of instruments are not much sensitive as compared to contact type. Then comes vacuum thermo elements. This type of instruments are mostly employed for the measurement of electric current at very high frequency of the order of 100 MHz or more, as these instruments retain their accuracy even at such high frequency. Then comes bridge type. These bridges are manufactured on the AC ratings, usually from 100 milliamperes to 1 amperes. And these two thermocouple are connected to form a bridge, which is shown in the figure. There is no requirement of heating element. The electric current which directly passing through the thermocouple raises the temperature, which is directly proportional to the I square R losses. The bridge works on the balance condition, at which there will be no current in the arm AB. The connected meter will show the potential difference between the junctions A and B. Then comes what are the advantages of thermocouple type instruments. This type of instruments accurately indicates the root mean square value of current and voltage irrespective of the waveform. And there is a wide varieties of range of thermocouple type instruments are available in the market. This type of instruments give very accurate reading even if at high frequency. The measurement of quantity under these instruments is not affected by stray magnetic fields. These instruments are known for their high sensitivity. So these are the advantages of thermocouple type instruments, and the disadvantages of thermocouple type instruments are the overload capacity of thermocouple type instrument is very small. So there is a chance to burn out of the wire. And the applications of thermocouple type instruments are used in temperature, current and voltage measurement. Then comes measurement of energy. We can measure energy by using rectifier type instruments, wattmeter, thermocouple type instruments. As energy can be measured at energy equals to power into time, that is energy equals to voltage into current into time. Thank you for watching this video.